After ensuring that the retaining wall is safe in overturning and sliding, we will now calculate the pressure distribution at the bottom of the base slab. So we know that the retaining wall is subjected to a number of downward forces like the weight of the stem, the weight of the base slab and the weight of the soil, and it is also subjected to a horizontal force due to the soil that is retained. Now these forces are applied at different points and we need to find out what is the point of application of the resultant from the toe. So that is denoted by x bar and it is given by summation m upon summation w, which we had calculated from the table. So the values of summation m and w are 287.655 kilonewton meter and 204.91. So on substitution we will get x bar as 1.4 meter. Now this 1.4 has to be in the middle 1/3 portion of the base slab. So when we divide the base slab, we know that into 3 parts, each one will be 1 meter. So 1.4 meters from the toe will be somewhere here. Okay, so that means it is lying in between the middle 1/3 portion, and this is done so that to avoid the tension in the base slab. Okay, so the eccentricity is calculated and it's denoted by E, and the eccentricity is nothing but the difference between the centroid of the base slab and the centroid of the resultant. Okay, so that works out to be 0.1 meter, which is less than b by 6. The maximum pressure at the bottom of the base slab occurs at the toe, and let us call it P max, and it is given by summation W upon B into 1 plus 6E plus B. On substitution we will get 82 kilonewton per meter square. It is very important that this value that we get has to be less than the soil bearing capacity. It cannot exceed the soil bearing capacity, okay, or else we will have to redesign it. So whatever pressure the toe is experiencing has to be lesser than the capacity of the soil. So in our case it is much lesser compared to the SBC, hence it is safe. The minimum pressure is experienced by the heel and it is given by P minimum, which is summation W upon B into 1 minus 6E by B. So we get a value of 55 kilonewton per meter square. Let us have a look at the pressure distribution. So this is the pressure distribution. At the toe we have 82 kilonewton per meter square. At the heel we have 55 kilonewton per meter square. In order to design the heel slab, we need to find out what the pressure is at B, at the point B. Okay, so we have divided the portion ABGH into 2 parts. One is a rectangle and one is a triangle. So BJ we know is 55 kilonewton per meter square, and on interpolation you will find out that GJ is 13.8 kilonewton per meter square, somewhere around 13.8 or 13.9 kilonewton per meter square. So BG will be 55 kilonewton per meter square plus 13.8 kilonewton per meter square, and this is 68.8 kilonewton per meter square. So this is the pressure distribution. Next we have to check for shear stress at the base of the stem. Now if we have a beam which is simply supported, okay, this is the axis of the beam, and we have a transverse force here, P. This transverse force meaning it's a perpendicular force, it is perpendicular to the axis of the beam. Because of this transverse force, the beam will experience shear. Okay, so any force which is transverse to the axis of the member will cause it to shear. Now in the case of a stem, the force which will cause it to shear is this force PH. Okay, so pH is perpendicular or transverse to the axis of the stem, and it might cause it to shear at this point here. Okay, so we need to find out whether it is safe in shear or not. So the force due to the force pH is given by Ka gamma into h square by 2. We have already done this before, and it is 67.68 kilonewton. That was the unfactored force. So the ultimate force after applying a factor of 1.5 is 101.7 kilonewton. Next, we calculate the shear stress, which is given by tau v. This is Fu was the shear force, whereas tau v is the shear stress. Okay, so it is force per unit area, which is given by Fu into 1000 divided by Bd. On substitution, we will get 0.2543 Newton per mm square. The area of steel that we have provided in the stem is 16 at 150 mm center to center. Okay, so to find out how much of area of steel we have provided per meter, we use this formula. So 1000 stands for 1 meter. AST is the area of 1 bar of 16 mm, and S is the spacing we have adopted. So it works out as 1340 mm square. Now let us look at table 19, which is the table for design shear strength of concrete, tau C. Okay, so please bear in mind, tau V is the shear stress due to load, whereas tau C is the design shear strength of concrete. Okay, so concrete also has some capacity to take shear. Okay, so this tau C is that design shear strength of the concrete. Let us have a look at the table 19. So this is table 19. Okay, this is table 19. You will see in the first column here we have 100 AS upon BD. So we have to find out what is 100 AS upon BD, that is the percentage of reinforcement. Okay, and when we calculate 100 AS by BD, we get 0.335%. So this is the amount or percentage of steel that we have provided in the stem. Okay, now let us go back to the table. So it is somewhere between 0.25 and 0.5. Okay, also we will go to the third column since we have used M20 grade of concrete. So now tau C we have to interpolate, and it is between 0.36 and 0.48 Newton per mm square. Okay, so it is this is not TC but tau C. Okay, so tau C is between 0.36 and 0.48 Newton per mm square. I have not interpolated here because we have getting a value of tau V as 0.25, okay, which is much lesser compared to how much the concrete can actually take. So the concrete can take somewhere between 0.36 and 0.48. That is M20 grade of concrete can take a minimum value of 0.36 and 0.48 for that percentage of reinforcement that is provided. Okay, therefore it is safe in shear. Next we calculate the design of the heel slab. Okay, let us design the heel slab. Again let us tabulate. So the loads that we consider here is W3 is the weight of the soil. We have already done this. Only bear in mind there is a small difference. In the previous table we found out the distance from the toe. Here we are going to be finding out the distance from the base of the stem, that is point B. So 132.52 is the weight due to the soil, and it's a rectangle with a width of 1.55, and the distance from B will be half of 1.55, which is 0.775. So the moment is 102.7, that is 132.52, and multiplied by 0.775 will be 102.7 kilonewton meter. Then we find out the self weight of the heel. It's just a rectangle of 1.55 into 0.45. So I'm talking about this portion here. This is the heel. Okay, and we get 17.4, and B is again half of 1.55. 17.4 into 0.775 will give us 13.48 kilonewton meter. Now these are the downward forces, and I'm finding out the total, and it is 116.18. Next we need to find out the pressure, upward pressure. Okay, let us go back to the pressure diagram. So first let us find out the pressure due to the rectangle A, B, J and H. Okay, so the pressure due to that will be 1.55. Okay, that is the width. This is 1.55 multiplied by the intensity of pressure, that is 55. Okay, 1.55 into 55, which is 85.25 kilonewton. Again, this is a rectangle and the centroid will lie at the center of its width, so 0.775, and the answer is 66.1 kilonewton meter. So this is of the rectangular part. The next one is the upward pressure due to the triangular part GJH. Okay, so it is this triangular part GJH. The base is again 1.55, whereas the height is 13.8 kilonewton per meter square. So we do half into base into height. Okay, so here this is half into 13.9 or 13.8, whatever the value is, and we get here 10.77 kilonewton. Now it is a rectangle, something like this, right? And this is 1.55. The centroid of this will lie at 1/3 of 1.55, which is 0.516 meter. So we get here 5.55 kilonewton meter. These are marked in red because they are upward, whereas the previous ones, due to the W3 and self weight, we have written in black because it is downward. Okay, so the total negative or the total upward pressure we get is 71.65 kilonewton meter. The maximum working bending moment, that means after we subtract 71.65 from 116.18, we will get 44.53 kilonewton meter. So the ultimate bending moment mu will be 1.5 times 44.53. It is 66.8. The area of steel, after putting it in this formula, we will get as 474 square mm. But before we provide for this, let us check whether it is more than minimum area of steel or lesser than that. So when we calculate, the minimum area of steel, as discussed before, is 0.12%. It works out to be 540 square mm. So the area of steel that we calculated in this step is lesser than the minimum steel. So we have to provide at least the minimum steel. So when we use 10 mm bars, we get 10 mm at 125 mm center to center. Okay, again we provide some temperature reinforcement, and we could provide it at say 8 at 300 or 8 at 250 mm center to center. Now let us have a look at the detailing. Okay, so the one marked in green here, 10 mm at 125 mm center to center, is the main reinforcement of the heel slab, because when we see the magnitude of the movement, the net movement was, in the downward direction. Okay, that is 44.53. So the heel slab will bend somewhat like this. So this is the tension edge, and that is why the main reinforcement is provided on top. The reinforcement marked in blue is the temperature reinforcement, and it is 8 mm at 250